On March 5, 1979, two Soviet spacecraft drifting through the inner solar system were hit by a pulse of gamma radiation so intense that their detectors went from normal background readings to 200,000 counts per second in less than a millisecond. The same pulse triggered instruments on 9 other spacecraft scattered across the solar system within seconds. Scientists triangulated the source using the arrival time differences between each spacecraft, and what they found made no sense under any physics they had at the time. The radiation had come from a dead neutron star in a neighboring galaxy, 160,000 light-years away. An object that was supposed to be cold, quiet, and spent. Something that by every model in existence had no mechanism to produce what the instruments had just recorded. Nobody had a good explanation. The data was published, studied, argued over, and ultimately set aside as an anomaly. It would take 13 more years before two physicists named Robert Duncan and Christopher Thompson built a theoretical framework that could account for what those spacecraft had measured. When they did, they proposed the existence of a new class of cosmic object, one with a magnetic field so extreme that it broke the standard picture of what a neutron star was allowed to be. They called it a magnetar. Most of their colleagues did not take the idea seriously. They were wrong. There are currently around 30 confirmed magnetars in the Milky Way galaxy. Estimates of the true population run considerably higher because most magnetars spend the majority of their existence in a quiet phase, producing no signal strong enough to detect from Earth. They are scattered invisibly throughout the disk of the galaxy, including in the neighborhood of the solar system, and the only time we know one is there is when it does something. When a magnetar does something, the consequences are felt across a significant fraction of the observable universe. To understand why, you first need to understand what a neutron star actually is, because magnetars are a specific and extreme variety of an already extreme object. When a massive star, somewhere between 8 and 20 times the mass of the Sun, exhausts its nuclear fuel, gravity wins. The core collapses in less than a second, the outer layers bounce off and explode outward as a supernova, and what remains is a sphere of almost pure neutrons, roughly 20 kilometers across. The entire mass of a star like the Sun, compressed into an object you could drive across in about 15 minutes. At that density, a single teaspoon of neutron star material weighs approximately 90 million metric tons. That is not a rounding error or a rough estimate. That is the measured consequence of packing stellar mass quantities of matter into a volume the size of a city. The crust of a neutron star is composed of a material that physicists have nicknamed nuclear pasta, which is either an inspired name or evidence that astrophysicists have unusually good coping mechanisms. At the densities found in a neutron star's inner crust, competing nuclear forces cause protons and neutrons to arrange themselves into layered sheets and long cylinders, and computer simulations of this material have found that it requires 10 billion times more force to break than steel. Graphene, the material that researchers spent decades describing as the strongest substance ever produced in a laboratory, requires about 100 times more force to fracture than steel. Nuclear pasta beats it by a factor of 100 million. It is the hardest substance known to exist anywhere in the universe, and it exists inside an object moving through our galaxy right now, probably within a few thousand light-years of where you are sitting. A standard neutron star already has a magnetic field roughly 1 trillion times stronger than Earth's. That is the baseline. A magnetar has a magnetic field somewhere between 100 and 1,000 times stronger than that. The number that results is roughly 100 billion Tesla. Earth's magnetic field measures about 50 microtesla. The most powerful MRI machine ever built in a laboratory operates at around 45 Tesla. A magnetar's field is stronger than that by a factor of approximately 2 billion. At that field strength, according to quantum electrodynamics, the vacuum itself begins to behave like a physical medium. X-ray photons can split into 2 separate photons. Virtual particle pairs that normally annihilate each other before they can be measured instead become briefly real and detectable. Hydrogen atoms in those conditions are compressed into cylinders roughly 200 times narrower than their normal diameter. The electron orbitals that define chemistry, that allow molecules to exist, that make biology possible, are simply flattened into needles aligned with the field lines. Chemistry stops working. The concept of a molecule ceases to have meaning. All of this happens not on the Magnetar's surface, but thousands of kilometers away from it, in open space. This is the object that a 1992 theoretical paper proposed might exist, that most physicists dismissed, and that the universe had apparently been building and operating for billions of years without asking anyone's permission. The mechanism that creates a magnetar, rather than an ordinary neutron star, depends on what happens in the first second after a core collapse. When a massive star implodes, the inner core briefly becomes an extraordinarily dense, rapidly churning fluid of protons, neutrons, and electrons, all spinning together and generating a magnetic field through a process similar to the dynamo that sustains Earth's own magnetic field. In most supernovae, this dynamo phase ends quickly. The field generated during those first seconds persists, but it stabilizes at typical neutron star levels, which are already remarkable by any earthly standard. In roughly 1 out of every 10 supernovae, the conditions are different. The collapsing core rotates fast enough, and the convective churning in the newly formed neutron fluid is vigorous enough that the dynamo amplifies rather than stabilizing. The magnetic field keeps growing for the first 10 to 30 seconds of the neutron star's existence, until it reaches magnetar levels. After that, the field is locked into the crust as the star cools and solidifies, like metal freezing around an electromagnetic coil. The star then spends the rest of its existence, up to about 10,000 years, slowly radiating energy from that locked-in field. Here is the problem. The magnetic field inside a magnetar is not static. It evolves over time, shifting and twisting through the crust in response to the enormous magnetic stresses involved. And because the crust is physically coupled to the field, the way Duncan and Thomson described it, the field and the crust are locked together like hair growing out of the scalp. When the field shifts, the crust is forced to shift with it. The crust resists. Nuclear pasta is, after all, the strongest material in the universe. But the magnetic field threading through a magnetar contains more stored energy than the sun will produce over its entire 10 billion year lifespan. When something that strong pulls on something that stiff, stress accumulates. Slowly, over years or decades, the strain builds along fracture lines in the crust, like tectonic stress building along a fault. And when the strain finally exceeds what even nuclear pasta can hold, the crust breaks. Geologists use the Richter scale to measure earthquakes. The most powerful earthquake ever recorded on Earth, the 1960 Chilean earthquake, measured magnitude 9.5. It released energy sufficient to power the entire United States for roughly 90 years. A starquake on a magnetar, driven by the sudden fracture of nuclear pasta under magnetic tension, would register at approximately magnitude 23 on the same scale. The crack itself is tiny by stellar standards, possibly just a millimeter of slip across the fracture surface. But a millimeter of slip in a crust made of material 10 billion times stronger than steel, under the force of a magnetic field containing more energy than the sun's entire lifetime output, produces consequences that are not tiny at all. When the crust fractures, it releases seismic waves that propagate through the neutron star at a significant fraction of the speed of light. Simultaneously, the fracture disrupts the magnetic field structure above the surface. The field lines, which had been held in tension for years or decades, suddenly snap and reconfigure, releasing their stored energy in a burst of gamma rays and X-rays that can last from fractions of a second to several minutes. The surface temperature during this event is high enough to vaporize hundreds of trillions of metric tons of matter in an instant. The entire event, from the first crack to the peak energy release, takes less time than a human blink. The magnetar designated SGR 1806-20 is located somewhere between 28,000 and 50,000 light-years from Earth, on the far side of the galaxy in the direction of Sagittarius. The distance is uncertain because it sits behind so much interstellar gas and dust that measuring its precise location has been debated in the scientific literature for 2 decades. Regardless of the exact figure, what matters is what it did in the early hours of December 27, 2004. A starquake had occurred on its surface. The exact moment of the quake itself happened somewhere between 28,000 and 50,000 years ago. The light from it was only now arriving. And at 21:30:26 UTC, that light hit Earth. The RESI satellite, a NASA solar observatory, had its detectors instantly saturated. The Integral spacecraft, a European gamma-ray observatory not pointed anywhere near the source, detected it anyway, because the burst was energetic enough to reflect off the Moon and register as a measurable secondary signal. The SWIFT satellite recorded it. The Mars Odyssey orbiter, then on the far side of the Sun relative to Earth, recorded it. Cassini, cruising through the outer solar system on its way to Saturn, recorded it. 11 spacecraft in total detected this event, and several of them were so overwhelmed by the signal that their instruments could not return useful science data for the duration of the burst. In the first fifth of a second, the Magnetar released approximately 10 to the power of 46 ergs of energy. Written out in full, that is a 10 followed by 45 zeros. During those 0.2 seconds, SGR 1806-20 was brighter in gamma rays than the combined light output of every single star in the Milky Way galaxy. For that fraction of a second, if you could have seen in gamma rays from outside the galaxy, there would have been a point of light where our galaxy was, outshining the galaxy itself. And then it was over, and the Magnetar settled back into its quiet rotation. The gamma-ray and X-ray pulse crossed 30,000 or more light-years of empty space, hit Earth's upper atmosphere, and partially ionized it. The ionosphere is the layer of the atmosphere that reflects radio waves, that makes long-distance radio communication possible, that protects us from certain categories of solar radiation. The 2004 burst disturbed it measurably, from a source on the other side of the galaxy. Scientists published papers characterizing the ionospheric disturbance. It was real, measured, and documented. A 2005 analysis in Nature calculated that if SGR 1806-20 had been within roughly 1,000 light-years of Earth at the time of this event, the gamma-ray flux would have been sufficient to destroy the ozone layer. The ozone layer, once lost, takes years to recover. The biological consequences of prolonged, unfiltered ultraviolet and gamma-ray exposure would not be mild. At a distance of about 10 light-years, the burst would have been bright enough to ionize the entire atmosphere. The magnetar that produced this event was at 28,000 to 50,000 light-years. The word safe is doing a great deal of work in that comparison, but it was, technically, safe. What the 2004 event clarified for astrophysicists was that the 1979 detection, the one that had confused everyone with its instruments and sat unresolved in the literature for 25 years, had been the same class of phenomenon. Another magnetar, another starquake, another giant flare. In 1998, a third such event had occurred from SGR 1900+14, a magnetar about 20,000 light-years away, powerful enough that a NASA spacecraft, the Near-Shoemaker probe, automatically shut itself down to avoid instrument damage when the burst hit. 3 documented giant flares from 3 different magnetars in 1979, 1998, and 2004. The universe had been running these events for billions of years. Humanity had been in the path of 3 of them in 25 years, and had only understood what it was looking at in retrospect, after the fact, decades later. For most of the 2000s and 2010s, astrophysicists were increasingly preoccupied with a phenomenon that nobody could explain: fast radio bursts. The first was detected in 2007 from archival data collected in 2001. and it appeared as an intense pulse of radio waves lasting a few milliseconds, originating from outside the Milky Way. Over the following years, more were found. Hundreds, then thousands. They came from all directions in the sky, from billions of light years away, and they shared a characteristic brightness and duration that suggested they were coming from very compact objects, releasing enormous amounts of energy in an extremely short time. The leading theoretical candidate was Magnetars, because the energy scales and time scales were consistent. But the evidence was indirect, and the sources were so far away that confirming any specific mechanism was essentially impossible. Then, on April 28, 2020, the Magnetar SGR 1935+2154, located roughly 30,000 light-years away inside the Milky Way, produced a burst that two independent radio telescope arrays detected simultaneously. CHIME, a large radio telescope in British Columbia, detected it. STARE-2, a different instrument in the United States, detected it independently at the same time. The burst lasted about 1 millisecond. Its radio energy output was consistent with the fast radio bursts that had been cataloged from distant galaxies. This was a fast radio burst, originating from a known magnetar in our own galaxy, at a known distance, with a known magnetic field and a known history of X-ray activity. In a single observation, 13 years of theoretical debate was resolved. At least some fast radio bursts, and possibly all of them, are produced by magnetars. This discovery reframed the significance of everything in the fast radio burst catalog. The signals being detected from billions of light years away, the ones that appear as millisecond pulses of radio energy with no obvious source, are likely magnetar starquakes in distant galaxies. Objects roughly the size of a city, composed of the strongest material in the universe, with magnetic fields 100 billion times stronger than anything a laboratory has ever produced, occasionally crack. And when they crack, the resulting burst of energy is detectable across a significant fraction of the observable universe. The universe is full of these events. We have cataloged over 1,000 of them. Before 2020, we did not know what was making them. The 2020 detection also raised a question that researchers had raised tentatively after the 2004 giant flare, but never fully resolved. How many of the events in the existing gamma-ray burst catalogs are actually magnetar giant flares that were misidentified? A 2005 paper in Nature estimated that a magnetar flare at the distance of nearby galaxies in the Virgo cluster would be detected by gamma-ray satellites as something indistinguishable from a short gamma-ray burst, the class of event astronomers had been attributing exclusively to neutron star mergers. The implication is that a meaningful fraction of the events filed under short gamma-ray burst in the existing archives may actually be magnetars cracking in nearby galaxies, events from objects far smaller and stranger than a neutron star collision, classified incorrectly because the instruments had no way to distinguish them at that distance. Set the hazard aside for a moment, because magnetars are also, by a significant margin, the most useful extreme physics laboratories in the universe. The conditions inside a magnetar, the densities, the magnetic field strengths, the temperatures, do not exist anywhere that a human experiment can access. Quantum mechanics and general relativity both apply simultaneously in the magnetar environment, and neither theory alone is sufficient to describe what happens there. Every observation of a magnetar event is a data point from a regime of physics that has no laboratory equivalent. The 2020 confirmation that magnetars produce fast radio bursts opened an entirely new window on the universe. Over 1,000 fast radio bursts are now cataloged, and the instruments used to find them are improving rapidly. Each burst encodes information about the magnetar that produced it, the magnetic field geometry, the properties of the crust, the structure of the surrounding plasma. The universe has been sending us these signals from billions of light years away, and we are now at the point where we can begin reading them systematically. The gravitational wave observatories LIGO and Virgo, which have spent the last decade detecting mergers between black holes and neutron stars, may eventually become sensitive enough to detect individual magnetars simply existing. A magnetar's magnetic field exerts such enormous force on its crust that even the strongest material in the universe deforms slightly, producing a tiny asymmetry in the star's shape. As the magnetar rotates, and most rotate multiple times per second, that asymmetry generates continuous gravitational waves. Detecting those waves would allow astronomers to measure the properties of nuclear pasta directly, the first real measurement of the strongest material in the universe that does not come from a computer simulation. On March 5, 1979, two Soviet spacecraft measuring Venus's atmosphere were hit by a pulse of gamma radiation from a dead star in another galaxy, and nobody understood what had happened. 41 years later, a radio telescope in British Columbia detected a millisecond burst from a magnetar in our own galaxy, and resolved 13 years of mystery about what produces fast radio bursts. The universe built these objects, scattered them through our galaxy, and they have been operating on their own timescales, releasing energies that dwarf anything else a stellar remnant can produce, whether we were watching or not. We were not watching in 1979. We are watching now. What we are finding, in the data from these events, is a picture of matter and physics under conditions that should not exist, in objects that have no right to be as powerful as they are, and that we are only beginning to understand.